Yeah, I think I got it. They should be able to see. Gonna resize it a bit. It would be like that way, so you would see that half of the board.
Yeah, it's only that bit I would use as a parse tree. I want to put on there and show it.
Okay, yeah.
Okay.
Yeah, that's good. We should be able to see the...
Okay, folks, let's make a start. So today we're going to be talking about parsing, okay, particularly context-free grammar parsing, because that's the main thing that we actually do, because we naively believe that natural language is context-free, as you're probably aware from what David was saying last week. Actually, natural language has got things that are a little bit beyond context-free, probably what's called index grammars. But we just cleverly ignore that. Well, we don't ignore it, but if we can do context-free, we're happy enough, because many of the things that we want to do will be sufficient in context-free, and it's sort of harder to do these relatively rare things, at least in English. So we're going to concentrate on context-free grammars. So remember what we're talking about. We've got these different levels of looking at phonemes or orthography into words, and then we're looking at how these words are joined together in syntax. Words are not there in random order, they're in a specific order, and each language has got specific rules about how we join them. They're somewhat soft rules, they're not always 100%. In some languages they're not as fixed as what they are in others. English is fairly stable compared to some other languages. It doesn't allow random word order, but you can still often change the word order. But there are somewhat standardized ways that words are expected to be, and the order that they're in tell you information about how the words are reflected, or the words are used with respect to the verbs that are around that. And this is something we'd like to be able to get. So what we're going to do is we're going to do context-free grammars. We're going to restrict ourselves to these because they're sufficient for most things. They're not actually absolutely everything, but they're pretty good. We're going to talk about recognition. Recognition is a task is given a grammar, does this sentence match that grammar? And parsing is given this sentence and it matches the grammar, show me the bracket, show me the structure that's actually in there. And these are not quite the same task, although you have to do almost the same things to be able to do that. The parsing algorithms really fall into two types. You can go top down or bottom up. You can say, I'm going to look for a sentence. What does the sentence have? Oh, it's got a noun phrase at the beginning, so I'm going to look for a noun phrase. Let's see if it's got a noun phrase in there. Oh, it's got a noun phrase. Let's look for the verb phrase that goes with it. So we can go top down. Alternatively, we can go bottom up. We can say, well, what sort of words do we have? Can we put any of them together? Oh, look, there's a noun and there's an adjective before it. Let's put those two together. Oh, look, there's a determiner before it. Let's put those two together. At some abstract level, it doesn't matter, and at some real implementation level, it really matters. Okay? So, for example, it's not unusual in speech processing to actually only do bottom up and not top down, because in speech processing, people don't speak in sentences. They're really, really bad at it. They're supposed to speak in sentences, but they don't. And we could say, Alexa, something, 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 and Alexa could say, you didn't say a sentence, so I'm not going to answer it. And people wouldn't like that. So what we do when we get a sentence with Alexa is we sort of try to chunk things together as much as possible and tries to piece together what's there into something that's useful, even if it isn't technically a sentence. So we're going bottom up looking for things. Okay? Sometimes that's not the right thing to do, and sometimes it's also more efficient to go top down and say, I know I'm looking for a sentence, so I'm going to look for the parse. Okay? We're going to talk about Chomsky normal form, CNF. Chomsky normal form is a particular simplification of context-free grammars. It's a way of saying the rules can only have two non-terminal daughters or one terminal daughter. It makes life much easier for processing. There's a way to be able to convert any context-free grammar into a Chomsky normal form, and many of the algorithms require it. And so, actually, often, not just that, but people who think about grammatical theories often end up thinking in Chomsky normal form. We're then going to talk about the first algorithm today. We're going to talk about what's called CKY Algorithm, the Koch-Younger-Kasami. Those of you who are still awake are going to note that the order of the names is not the same as the order of the letters. And I noticed this on the slide some years ago, and so I looked it up, and then I thought, wait, no, that's wrong, it should be the other way, so I fixed it. And then I looked again, and then I looked it up on Wikipedia, and then looked back to the original paper, and the answer is, yep, both ways are fine, okay? So it's one of these algorithms that either order of the letters is just fine, okay? And it appears in both orders, and you should just deal with it. And it's not you forgetting, okay? Which is pretty cool. I think it's a good algorithmic name where you flip it arbitrarily. Okay, let's think about this sentence. The student who was taught by Alan Black won the prize. Okay? Now, I have to first admit that I did not construct that sentence. Okay? And I don't know why you might think that I would have constructed that sentence, but I didn't construct that sentence. Okay? But it's there now. So look at that sentence. The student who was taught by Alan Black won the prize. Who won the prize? I'm going to ask you that, even though it's written on the thing. Okay, so supposing you're going to use some naive thing that looks for a subset of words. Okay, what you're going to find out is you get this subset of words that says Alan Black won the prize. And Alan Black won the prize is actually in that sentence, so that must be correct. Eh? Well, no, it isn't. It isn't correct because there's a relative clause in there. And it's the student who won the prize, but the student who was taught by Alan Black won the prize. But Alan Black won the prize is actually a subset of that sentence, but that's not what that sentence means. And the question is, why can we deal with that? And the answer is syntax. The answer is parsing. Because if you parse that sentence, you're going to get to see that the first noun phrase that appears in that sentence is the student who was taught by Alan Black. And that whole thing, and what is that noun phrase? It's the student, it's not the Alan Black bit that appears at the end. Okay? So we need to know that bracketing in order to be able to answer that question, unless we have something else that can tell us about, it's not the words closest to won the prize that is actually giving us the answers. So that's why we're doing it. Now, yes, sometimes that doesn't matter, okay? Especially in relatively short things, especially in things like dialogue, it might not matter, but it often does. And so it would be good if we could actually get that structure out of there, so when we ask the question, who won the prize, we get the correct answer, the student, rather than Alan Black. Okay, context-free grammars. Okay, you will remember this. So we've got a vocabulary of terminal symbols, a bunch of words. We've got a set of non-terminal symbols. You could think about them as variables. We're going to write those in uppercase letters. We've got a special symbol, almost always S for sentence, okay? And we've got a bunch of production rules where X goes to some string of forms. And X is always going to be a non-terminal, and alpha is going to be some combination of non-terminals and terminals, okay? It's going to be a string of them, 0 or more. Actually, I don't like having 0, but you can have 0, okay? If you really want, okay? So it's a rule. I've got a thing that goes to X, Y, Z, okay? So that's what it is. Importantly, for context-free, that there's only one thing on the left-hand side, okay? There's no other conditionings or context with respect to the left-hand side. It's just one thing. So if I have an N, that N gets expanded or can be rewritten as any of these other forms, then it doesn't matter the context that N is in. That's the context-freeness about it. That's why it's called that. So if we've got a sentence, bunch of words, W1 to WM, and we've got a context-free grammar G, there are two things that we might want to ask. One is recognition, and that is true or false if the set of words, the sentence, okay, is in the language that G describes. So we have some grammar, it describes a language. That could be an infinite language. In fact, it often is an infinite language. It doesn't have to be infinite, but it often is. And we want to know if it's in that language, okay? It's sort of what we have the grammar for. We want to know whether it's in that language. parsing, okay, what we like to know is one or more derivations of W. Derivations are, show me your working. Basically, which rules were used and when, and what were the expansions. Rather than just going yes or no, I want to know which rules, and where did you do it, how did you expand them to be able to get it. This is often drawn as a tree, because a tree has that information. It doesn't have to be drawn as a tree. It can be actually given as a set of what's called production rules, so it shows you what actually gets expanded, and I'll draw that on the board in a minute. We can go top down or bottom up. Top down, we start with S and we start expanding the S and trying to find the things that are down there. Bottom up, we can look at the words and then try to join them together, okay? I already told you that maybe in speech, sometimes we care about bottom up because people are not really forming sentences, but we'd like to find the noun phrases that are in there or clump things together in some way. Top down is often what we do. Actually, in programming languages, we almost always do top down, but the reason that we almost always do top-down in programming languages, I mean like parsing the C programming languages or Java or something like that. And the reason we go top-down is because the syntax of these languages is specifically designed to be easy to do top-down parsing. It usually is the case that you can look at the next symbol and you can decide what the next expansion is. This is often called FF1. Probably been taught that in programming languages elsewhere, but human languages are not like that because that's too easy. So often you need to know a little bit of context, and there might even be confusable, ambiguous things at the beginning of a sentence that you don't know how to complete them until you get further on in the sentence. Quite common. Implement recognize this is relatively easy. But we want to try to hypothesis in terms of search rather than some just other algorithm. We're going to give a bunch of different text. So we're going to search the space for it. So we're going to take a task. We're going to do something which will generate other subtasks that we're going to put in an agenda. And then we're going to take the next one off the agenda. We're going to keep doing this until the agenda is empty or I've found a complete parse. The reason we want to keep it as a search is we might want to manipulate that agenda and doing different things. We want to choose the most likely thing rather than everything, because sometimes searching the whole space is not worth it, it's too big. We want to find the most reasonable parse as quickly as possible, but not search for everything. But this idea of, say, if we're going top down, we take the S, we expand it with whatever rules expand S, and all of these subparts then get put back onto the agenda. Here's a grammar. It's a very simple grammar. Okay, and it really only deals with aspects of flight, so booking flights. What I'd like you to do is, can somebody give me a sentence for this grammar that's valid for this grammar? Come on. Sorry, I'm doing it, yeah.
I book. I book.
I book. Yes, so that's I is a noun phrase. Okay, so the S goes to NP, the NP goes to pronoun, the pronoun goes to I, and the VP, back to the VP expands to verb, and verb expands to book. Okay, so imagine your goal in life, okay, is to book tickets. That's what you do. You book tickets, okay? And so I come up to you and say, what's your goal in life? You would say, I book, okay? And that's what the sentence means. It's a little unusual, okay? But, you know, whatever you want to do, that's just fine, okay? What's weird about it is that the word book is really a transitive verb and not an intransitive verb. So you really, I book a flight, okay, is the more common usage, but it can be reduced to I book. Okay, can somebody give me another sentence?
Does she prefer me?
What?
Does she prefer me?
Does she prefer me? What an excellent philosophical question. Okay? I'm always amazed every time that I really expect, I book a flight to Boston. Sorry, Houston, I think is the one that's in there. But people always come up with cool ones. Okay. So normally at this point I ask for somebody, can somebody come up with a sentence that's in this grammar that isn't in English grammar? Does me prefer flight? Okay?
I think just any verb is the entire sentence, because there's verb phrase and then
Oh yeah, you're right.
verb, so just include is
Yeah, you're right. You're absolutely right. So single verbs. So maybe you could have the instruction book, okay, which means go and book them, but include, it's a hard thing to, prefer. Okay, I'll prefer what, but so it's a little weird. So yeah, there are things here that are not in English. Okay, can somebody give me a sentence which is in English which is not parsed by this parser? Yes, okay, but that's almost in the grammar, okay? So a sentence like to be or not to be, that is the question, is also not in I assume. Should check that, but I don't think it is, okay? But so there's lots of things missing, and there's lots of close things that sort of should be that, but we're ignoring that for the time being. This is defining a particular language. Okay, this grammar describes a language being the list of sentences that this stuff. Is there an infinite number of sentences or a finite number of sentences? You sure? Isn't a recursion through the PP? Yes, yeah. So you can go to Houston, to Houston, to Houston, to Houston, to Houston, to Houston, to Houston. Okay, Houston's really nice, but I'm not sure they want to do that. I also know that it's got NWA as the flight. This comes from the Juraski and Martin book, and NWA hasn't existed as an airline since, I don't know, whatever, Northwest. Delta, I think they are now. Anyway, so this is not a comprehensive thing, but we have this grammar and we'd like to find out whether things actually match it or not. Okay? So in a recursive descent, top-down parser, this is often what we do with programming languages, and it almost always works with programming languages, because programming languages have specific restrictions in them that make this work. So they actually really try to be able to make sure that the next individual word allows them to make decisions, and you don't have ambiguities. Yeah, you have the dangling else, but let's ignore that. But this idea may or may not work in particular programming languages. In this case, it actually does work, but it's not guaranteed to work for all context-free grammars. Okay, so we can do our recursive descent top-down parser. What we're doing there is we're saying, I'm going to look for an S. I'm going to look for all of the ways in the grammar to expand S, and I'm then going to do each one of those rules and then see if I can expand that until I eventually find the thing at the bottom left-hand corner that I'm looking for. And if I find that word, I'll accept that word, and then I'll try to do the next part. Okay? Now, here's a simpler version of the grammar, and what I want to do now is actually to show in this very simple grammar, okay, what a derivation actually is. So at the beginning I said that there's recognition where you go true or false to say what's in the grammar, but I also care about what the derivation is. And derivation, I mean, is I want to see the list of expansions that are actually happening in order to be able to do this. So there is 2 sentences that this does. No, there isn't. There's more than 2, but there's 2. So you can have John flies Delta, and that's the sentence I'm going to do, but you can have John flies Joyce, John flies Johns, you can have Delta flies Delta, and you have Delta flies John. All of those are in this grammar, but we're going to do the sensible one of John flies Delta. And so what I'm first going to do is I'm going to do this. I should write this at the bottom if I'm going to do top down, bottom up. So I'm going to do top down first, okay? And so for top down, I'm going to start with S, okay? And given the rules that I have, S can expand to NPVP. So NPVP. I can replace the S with the NPVP. That's what the rule means. Okay, there's no tricks going on here. what I can then do is, well, I can't match anything at the bottom. Oh no, I can, because NP can go to John. Okay, so I can go to John and VP. Okay, VP can expand to V and NP. Okay, so let's just draw these things in. V and NP. V can expand to flies, and NP can expand to delta. Okay, very simple. Okay, you could write a program to do that, which is what we're going to talk about, is how to be able to write programs to do that. This is what's called a derivation. So you start with something, you replace something, you show all the rules that are actually happening in order to be able to do it, not just whether it's true or false in the case of grammar recognition or not. And this is often what we want. There may be more than one way to do it. Now, technically, even in this, there's more than one way to do it, because we could have expanded this bit before we expanded this bit, so there's a ordering issue. It doesn't matter with the end result in this case, and sometimes it does and sometimes it doesn't. Okay. We of course can also go bottom up. Okay, so what we would do in bottom up is we'd say, well, we have John. Is John the right hand side of any of the rules? And the answer is yeah. There is a right hand side of one of the rules, so that we can have an NP. Okay, and then we could look at flies, and we could look at flies, and we get a V, and we look at delta, and we get a NP. Okay, does NP go anything? Well, yeah, we could find an S. Okay, but we need to have a VP as well, so there has to be some sort of VP thing here, but we haven't got that yet. The V in there, oh, we can do that. We can join these two together and replace it with a VP. Oh, these VPs can actually be the same thing and go up to the S. So derivation is telling you all the rules that you've applied. That's all. Many of the algorithms, not all, but many of the algorithms require the grammars to be in what's called Chomsky normal form. Okay? This happens so often that many people think that context-free grammars can only have binary branching, 2 non-terminals or 1 terminal symbol. Okay? Because almost always it does. Okay? Most of the machine learning stuff we do, we just restrict it to that because it's easier. It's not really the best way to describe human language. Sometimes you want to have 3 or 4 daughters, but there's always a way to convert. Okay, so there's no power loss in the complexity of the grammars that you can, of the languages you can describe if you go into Chomsky normal form, and so people just go, yeah, it's the same. And, you know, it's, at some level it's the same. So often people do this. So if you want to sound intelligent when somebody's telling you about a acute parsing algorithm, ask them whether it requires the grammar to be in Chomsky normal form or not. Okay? Because it is sort of important, at least it's a restriction, but it's not, you know, the end of the world when we're actually doing it. And the only restriction in Chomsky normal form is 2 daughters, both of which have to be a non-terminal, or 1 daughter, and that has to be a terminal symbol. Okay, so it really means it's binary branching rules. And you can trivially do that if you have a grammar that's got 3 things on the right-hand side. You just introduce a new non-terminal. In this case, we called it x2, and we just said that x goes to a plus a x2, and x2 goes to bc. That's going to recognize the same grammar. The trees, the number of derivations is going to be different, but you know, you could work out to put them back together again if you had to put them back together again. Okay. We can rewrite the grammar that we had before into Chomsky normal form. Okay, and it's pretty easy to write rules to do that. It's not a hard thing to do. Okay, and this makes it easier for some of the grammar, the parsing systems that we actually deal with. Okay, the reason that we're doing this, because one of the first parsing algorithm to look at is the CKY algorithm, and the CKY algorithm requires things to be in Chomsky normal form. That's a restriction, but it's not much of a restriction. And what we can do is we can actually do parses and find out the parse tree by having things only in Chunky normal form. Okay? I'm going to talk about the algorithm in a number of different ways. I know that all of you have got different ideas of what the best way to understand an algorithm is. I have to admit that my way of finding the best way of understanding an algorithm is implement it. Okay? And so all of these descriptions might not work for you, so go and implement it. It's not very hard. But I'm going to describe it in a number of different ways, both in pseudocode here, by running through an example and giving you the logical forms of the things that would actually allow you to do this. Pick whichever one is appropriate, or go and implement it. That's just fine. I'll spend about the next 10 minutes on this. If you can implement it on your laptop in the next 10 minutes, that's pretty cool. Okay, don't do that. We normally, when we're displaying this, or maybe only when we're teaching it, we put in what's called a chart, C-H-A-R-T. In fact, the next algorithm I'm going to talk to is actually called chart parsing, so it has this representation. You can think about it as a big matrix, okay? This is maybe the diagonal of the matrix, and we're going to deal with the things at the top right, okay? What we're going to do is we're going to see how we can join these things together. We're going to do bottom up. We're going to join these things together in order to try and find an S that covers everything. Notice I said an S sentence that covers everything. Sometimes there can be funny subsets of the sentence which are also sentences but don't include all the words, and that might not be right. And so the condition is not just finding any S's that are in there, sentences that are in there. The job is to find sentences that cover all of the words. Okay? So we write in the diagonal the words that we're actually dealing with. Book this flight through Houston, which matches the grammar. I know it's in the grammar. I mean, we could do an example without not being in the grammar, but it would be less interesting. Okay? And the first thing that we do is we look at the top right, and we're going to go through the top right, and we're going to go through all of the possible nodes that could be in this imaginary tree that we're building, and fill in any of the rules that could give the word book. So we look at the word book, and we look through the rules that are there, and we discover that there's a noun goes to book somewhere. It's nominal, it's called. It's not actually called. It's nominal to book. Okay? And so we have the word book there. Okay? But book is also a verb, okay, which you thought was an excellent verb, okay, and it is an excellent verb, although it's a little weird on its own. But theoretically, there's a sentence within this grammar, which is the command on its own. Book, you know, Picard, going, engage. It's the same thing as that, book, but you probably would never say that. So it's also potentially a verb, okay? That's not the right answer. It won't take part in the thing there. But it doesn't know that at the time, so it has to do that. Okay? So for each of the words in the sentence, we can actually expand what their non-terminals actually are. And of course, the one at the end is also an NP. Houston is a proper noun, and a proper noun then goes up to a noun phrase. There's nothing that can be joined at the top of trying to put book and this together, because that's not a constituent. Okay, but this flight is a valid NP by putting together the determiner and noun. There's nothing that can put flight and through together because they're subparts of other things. There's nothing that can put this flight through together. There is something that can put through and Houston together because that's a PP, so we get a PP for that. There's nothing that puts flight through Houston together, but there is something that put this flight through Houston together, which gives us a noun phrase which is joining together that top noun phrase and the PP that's below it, because that makes a noun phrase, a bigger noun phrase, with the prepositional phrase through Houston. Okay? Then we can form a VP, which is along the lines of, oh, I was wrong about this, which forms the sentence, book this flight through Houston. So it is a command, it is a verb, and we have a big verb phrase that covers everything. And it's also a sentence that covers everything. Okay? And we also have a wait a minute, sorry, I'm reading that wrong. The VP is dealing with the book this flight through Boston, but the sentence is dealing with book this flight, which is a sentence, but it's not a full, it's not getting all the words. So the end sentence gets not just a sentence that's all the word, sentence that is valid, but also uses all the words, and that's important. So what we're doing is we're basically going through each of these nodes and finding out what can we combine at that point and getting the list of things that combine at that point, and then moving up to the next level and doing it, moving up to the next level to do it. So what we have to do is we have to visit every single potential node and find out whether there's anything below it that can be combined. Okay? We'll come back to that because that tells us something about the complexity. Okay? So here's the pseudocode. Here's the logic equations for this, and basically all we're doing is if we look at the bottom end, so the not the very first clause, the second clause, what we're doing is we're adding in the non-terminals, and then what we're doing is if the two things underneath us can be combined together, and there is a rule that combines them together, and then we combine them together. Complexity in the worst case is actually n cubed times the number of rules in the grammar, but we have to check everything, okay? So the best is the worst case, that's not ideal, okay? Often other algorithms are a little bit better in the average case, although it's hard to be better in the worst case for anything, because you really sort of have to look at everything in the space of the words. So that's context-free grammar parsing, the CKY algorithm, but realistically nowadays we no longer do simple context-free grammar parsing. We at least do probabilistic context-free grammar parsing, where we actually want to care about the probabilistic chances of each of the rules, because they're not equal. Okay? So we only care about weighted parsing. Okay? So here we have a sentence, book the dinner flight versus book the dinner flight. Okay, and these have different parse trees. Could somebody explain the difference between the meaning of these two sentences?
You know, the left-hand side is treating like the dinner flight together as noun phrase, while
Yes.
the right-hand side treats the dinner as one noun phrase and
Yes.
flight as the second.
So can you give me a scenario where the second one is? Because the second one is the one that's weird.
Okay.
So imagine that there was a student called Light. Okay, that's her name. Okay, and we're going to get them to book a restaurant. Okay, and we weren't very sure they were going to book the restaurant for dinner or for lunch. But what I could do is I could say to the student, book the dinner flight. So the person who is called Flight, yeah, it's a new one, okay, is being instructed to book the dinner. Okay. Well, the first one means book the flight that has the dinner. Okay. And probably we like the one on the left more than the one on the right. I can think of both circumstances that you would use the one on the left rather than the one on the right. But they have the same words, and within the grammar that we're dealing with, both of which are valid. Yeah?
I guess, in general, do punctuations not include punctuation? Because I wouldn't write the right side sentence.
So there's an excellent question. Why isn't there punctuation there? Because it would make it much clearer. So yeah, you would often put punctuation in there, but remember, if it was speech, you don't get punctuation out of the speech recognizer, because the speech recognizer doesn't help us there. Actually, that's not true. Sometimes you get it out of it. You're right. There's punctuation missing there. Yes, I'm also deliberately selecting a really weird example. Okay, so it's not ideal. Although ambiguities in sentences are incredibly common, and most of the time you never see them. Okay, because you in your brain have a bunch of rules that have some probability next to them, and so you're choosing the one that's the most sensible reasonable interpretation given the circumstance that you're in. But the machine's stupid, and the machine ends up finding these things that are not reasonable. And so what we'd like to do is we'd like to add some probabilities into these in order to be able to get it to find the right thing. Okay? So what we can do is to add some probabilities, as if by magic. These get the right result. So where did I get the probabilities from? Well, it's very clear I got the probabilities from the Juraski and Martin book. But where did they get the probabilities from? Okay? And the answer is they sort of made them up, but they didn't quite make them up. Because you can actually work it out. So imagine that you have a large set of data that was already parsed. What you can do is you can look at how often each rule is used and use that to be able to calculate the probabilities. Okay? David's going to talk about that next week. He's going to talk about how you can get probabilities from corpora of data to be able to build probabilistic context-free grammars. At the moment, we're just going to assume that these numbers are right, because they are, and we're going to use them in the form. So if we do that, and we actually add the probabilities to each of those, what we end up getting is the one on the left has got a slightly smaller, sorry, no, it's the other way around. Yes, slightly smaller, because it's 10 to the minus 6 rather than 10 to the minus 7. 10 to the minus 7 is smaller, so the one on the left is more probable, and so that's the right answer. Well, at least it's the more probable answer. It might not be the right answer, so you should always be aware of that. Okay? So all we need to do is we need to modify our context-free grammar to make each rule, okay, have a probability. Okay? For each production, what we'd like to be able to do is add some additional, oh wait, that's just the normal one. What we want to do is we want to modify it to say that each rule has got some positive weight for that particular probability. And much more importantly, the probability, so for the expansion of S or NP or PP, that the sum of the probabilities of all of the rules come up to 1. Okay? We want them normalized to be actual probabilities. Okay? And that's what we say at the bottom. So the sum, for all x where there is a rule, the sum of the probabilities of these rules has to equal 1. Okay? So our algorithm has to change, but it doesn't have to change much. What we do in the weighted form is we just include the same combinations that we were doing, but we just keep track of the probabilities when we're doing it. And that works. There's nothing fancy going on here at all. Getting the probabilities is still a sort of issue, and often there can be funny interaction things that go on that can make it non-context free, but we're not going to talk about that. And for the logical form, we can actually do that. So we can end up with the probabilities. I'm not going to put a list because I want to do that. So we've talked about CKY as being a context-free grammar parsing. We talked about expanding it to be probabilistic. CKY is restricted to being Chomsky normal form. So what happens if you don't want to be Chomsky normal form? Well, there's another algorithm called Earley's algorithm, and Earley's algorithm does not need your rules to be in Chomsky normal form, and it's called the Earley's algorithm not because it's early in the day. It's called the Earley's algorithm because it's named after J. Earley, who got a PhD from some small university in Pittsburgh called Carnegie Mellon University. You might have heard of it. But he got it a long time ago. Okay, so his PhD was in 1968, which even for me is a long time ago. It was around, well, I wasn't in Pittsburgh in 1968. I was, eating haggis and playing bagpipes in Scotland in 1968. It's whatever it is that we boys do there. He's still around. He's a self-therapy advocate. He doesn't work in natural language processing. And in fact, I don't know anybody who knows him from his time where he was at CMU. And I've asked people because I thought, there must be somebody here who was around at the time. And there are a few faculty who are been in those days, but nobody, because it was a long time ago. But Earley's algorithm is the standard algorithm that people use for doing parsing of generalized context-free grammar. Okay? And I have to say that my own masters was actually a hardware implementation of his algorithm. So I built a hardware, like a little chip, that could do parsing on a chip in parallel to be able to do the parsing algorithm, which was way cool at the time. I have to also admit that the chip didn't work at all, okay? But that's a different problem. But I at least designed it and made a physical chip, and I have it in my office somewhere. And if you look through a microscope, you can see my name on it, but you can also see that the chip doesn't work. But that's a different problem. And this algorithm is still used, actually, rather interestingly, even, 50 years later. So if we've got the same grammar as what we've been doing before, allows arbitrary contradictory grammars. You can have top-down or bottom-up. You can do both of those. It's not really a problem. Again, fills in a table. This is typically called a chart. Earley's algorithm is also called chart parsing, interchangeably. He did not call it Earley's algorithm because most people don't name their own algorithm after themselves. It's people later on that use their name to do it. So he called it chart parsing. What you do is you create a bunch of vertices which have the core words between them. Do I have an example I'm actually going to do? Oh, yeah. I can do the same one that we did before. What we are doing is we now want to have an explicit representation of us interpreting the rules. What you could do in the CKY algorithm in the chart is there was one place where you could put, yep, that rule is there, or no, it's not there. Now we have to care about, we're going to recognize the subparts of each rule, the daughters of each rule, and we have to know where we are recognizing as we're moving along. Okay, and we do this with what's called a dotted rule. So we have a representation of the rule, and we have a dot that represents where I've recognized so far. So I'm going to draw on the board how to do that. Okay, these are arguably states, and so what we have is we have sentence goes to dot VP, which means that we're looking for a VP, but we're at the very beginning. If the dot was afterwards, it would be we found a VP because the dot's at the end of the after the VP. For the second one there, that we've recognized the determiner, but we haven't recognized any nominal. And the last one, we found the full VP because we found a V and an NP. The dot's telling you where you are in the particular form. So let's actually do this on the board. There's a couple of high-level rules that are in let's move on to that. So the first thing is, given all the words, we have to be able to add edges for these base words because we're going to use them in our form. So there's going to be vertices between each word, and there's going to be insertion for each of these. I'm going to draw the edges as a line. This is going to be labeled as an NP, okay, which is really the NP goes to John dot, okay, because we've recognized that. We have a V goes to flies dot, and we have a NP goes to delta with the dot at the end. So if we're going to start, how we're going to start is we're going to start with an S, and so we start with an S, okay, and it's going to start in the beginning because that's where we're going, and it's going to end at the beginning, and the sentence goes to dot NP VP. Okay, so that representation, which is probably hidden beneath the screen for the people at the back, can you see the thing at the back? Maybe not. So the S goes to dot NP VP, okay, because we're looking for an NP and a VP, and the dot's telling us where we're looking. And that's the first thing that we're starting off with. What we now want to do is we want to expand that, okay, and so, well, we're looking for an NP, so why don't we do insertions for the NP? So we're now going to do insertions for the NP. So the NP, okay, can go to NP goes to dot John, okay, and there's another one which goes NP goes to dot delta. We look at this one, we're looking for something that delta, we don't have a delta that starts here, but we do have a John that starts here, okay, a John, and so this rule and this edge can combine to form a new edge, which is going to be this one here, and this will be the NP goes to John with a dot at the end. So now we've got the NP and we've recognized the whole John, and we have an edge that goes from 1 to 2, okay? We can then take this new NP that we've recognized and we can get another S for this one because this one can move along, and we can now have our S goes to NP dot VP. Okay, so we've now got the dot in the middle because we've recognized the NP. Now the VP, I want the VP, and I'm ending here, so I know them at this particular node, and I want to find out how to be able to expand the VP. And if the VP, I can insert another one there. I can say VP goes to V, the dot at the beginning, and then I can say, oh look, I've got a V. Okay, so I can have another edge that can do the VP goes to V dot, because we've recognized that one should go up and down here because we're recognizing the VP for the V that covers the whole flies. And so I have a VP that goes to a V with a dot, so that completes the VP, and now that can fit on that one. Okay? No, we can't. NP on here. So we have an NP, and the NP we can start here, and we can say there's an NP goes to dot delta. And the dot delta can join with a complete delta, so we can have the complete thing with the delta at the end, and the NP can join with this. And then there's going to be another one that goes for the VP from here down to here. It does VP goes to V NP dot. That VP can join with this one to get a sentence that goes all the way around from the beginning to the end. That can be S goes to NP VP dot. So what we're doing with that dot is, as we are recognizing the individual parts of the rule, we're moving that dot around. And every time we're in the thing of what can I join together at this point, I want to find something where the dot ends, because that's my end point, and I want to find something that starts there, is either completed so I can combine, or I can then go and search for other things in the grammar to do it. So there's actually these three parts that actually happen. There's the scanner part where I'm actually doing the insertion of the lexical items. Okay. There's the predictor part. It's like I need an NP, I haven't got one. Let's go and look at the grammar and let's expand all the NPs and put the dots at the beginning. Okay. And then there's the completer where I finished something and can I join it with something else in order to be able to join it. Okay. This algorithm is pretty efficient. It beats any of the other algorithms. There are some things which can do things slightly faster, but they don't guarantee to find out everything. It's been hard to beat as an algorithm, and people don't really do it. It can be parallelized, which is why I did it as a chip that didn't work. No, I did it as a chip. It was supposed to work, not that it didn't work. That's the example that I was doing. And so here in the slides, we've got our edges that we're building non-graphically and showing the things. So the first stage, these are the basic insertions. These are after the next stage where we're using the scanner to be able to do it. These are the ones where we're using the scanner and completer. Here's the scanner and completer, and the scanner until we actually get the end result. Okay. Here's another run through exactly the same thing. Okay, book this flight through Chicago, and what we have again is we're trying to find S, which we go from the position 0 to position N, so that we've got root, a thing above S, and we're trying to look for an S at the beginning, and so at each stage we're adding in all of the rules where the bracketed forms are the beginning and end points, and the columns we're putting in where they actually end. So here we recognize book, which we can then fill in for VP to v.np, etc. Okay, so we can get to see all of these. We can think about this as a theorem proving problem logic. So what we're really saying is if there are these two things exist, then the other things exist. And in fact, this algorithm is sometimes used for theorem proving. It's also used for object recognition in 3D space, because basically you recognize a bunch of components that join together into some supercomponent. This is a really good efficient algorithm for searching the whole space and finding out whether they actually join. So this works for, it's often called the tableau method in theorem proving, and it's sometimes used in vision, especially if you've got complex objects that join together into single objects. This is a very efficient way of being able to build that form. What's the runtime complexity? 10 squared. Memory is relatively big. Possibly, there are PhDs from 20 years ago, not 50 years ago, that tried to make this faster. And you can't in general, but you can for the common cases, and so you can maybe do something, because often you end up doing things in this algorithm that lead to nowhere, and you can maybe detect that in advance. If a rule has got 4 subcomponents in it, and you're at the end of the sentence, there's no point in actually doing it.
What is pandas? Is this the number of words in the sentence?
Yes, so the end is number of words in the sentence, yes. Yep. What about getting the trees? Well, you can get the trees, so can you actually extract from that mess that I drew on the board, can you actually get the trees of S goes to NPVP and do that? And you can if you record which edges were joined to be able to form one. So every time you do the completer step, where you're taking, I found a VP, I was looking for an NP, I've got the NP. When you do it, you record which NP you actually found with a pointer to it, and then you can just recursively trace down and end up with a parse at the end, and an actual tree at the end, and so that's pretty efficient. You have to be a little careful about this. There's some arguments in context-free grammar parsing where sometimes people want to write a rule that says S goes to S. You might think that's a stupid thing to do, and usually they don't write the rule quite as explicitly as that. Often they say S can go to a question, a command, or a declarative, and then later on they have declaratives can also go to open sentences, and so you get a loop in the expansion. Okay, and this is technically valid in context-free grammar, but it could give you an infinite number of parses. Okay, the algorithm stops. Okay, but when you try to print out the parse tree, it prints out the parse tree, and printing out an infinite parse tree is never a good idea. Okay, because it prints forever. Okay, you can do tricks to detect that and make sure that that doesn't happen. Most people in linguistics, computational linguistics grammar, don't want that to happen because that's not what they meant. Okay, and so there should be fixes on there, and so you can do tricks to be able to do fixes to stop that from happening. But really, when you implement, it can happen, and so the whole thing runs. It says, I found 17 parses, would you like them to be printed out? Yes, and that's it, because I'm going to print them all out. Each of them is infinite, and you have to wait some time for that to be able to appeal. So that's something that you have to be a little careful about. Which you don't get that problem in Chomsky and Arnold form. Okay, so it's an advantage, or it's just something you actually have to care about. It's not really fundamentally a problem. It's pretty easy to catch because after the first time it happens, you write the code that stops it. So let's go back to parsing as search again, because this is quite a good way of looking at it. So what we're going to do is we can take these edges. Every time we get an edge, we put it on an agenda, and at each iteration we take the top one off, or the bottom one, or the most likely one, or something, some definition, some selection criteria, and then we do stuff, and that will generate more edges that you put on the agenda. This allows us to talk about this as a search space, because what we're doing is we're searching the whole space of all these things that we're going to get, these edges that we're getting, and it works pretty well, it's pretty efficient. You can do optimizations on the agenda itself. You can definitely prune it so that you can ignore the ones that aren't going to complete, and so you can make it much more efficient. And you can talk about the strategies you're doing to solve it independent of the particular techniques you're doing in joining things. I should add that actually in many real grammars, we don't have nice little tokens like NP. We've maybe got an embedding, a bunch of random floating point numbers, or we've got some complex structure that's got more information in it than just the NP. It's maybe got the number, the person agreement, etc. in it, that allows us to do more interesting things efficiently. So often it's more complex than just a simple symbol. The probabilistic stuff, just as easy, it's not a problem, just put all the probabilities in. And in fact, once you put the probabilities in, what you can start doing is you can actually start pruning your agenda to look at probabilities. You don't know the probability of the overall sentence, but you will know something about the likely probability of the subcomponents. And that allows you to make choices about which thing to do next. And this can be really, really, really efficient. This is a really good way of trying to make things much more efficient in parsing. You may think that when you're looking at a sentence, there's only one or maybe two parses, but for most grammars, there are hundreds of parses, and maybe even thousands of parses, in ways that one, are just not right, or two, it doesn't really matter, okay? And it's always a good idea to get the most probable one if you can, or maybe the top 5 most probable ones, and you can process later to find out whether they're sensible or not. And so being able to choose what you're going to do next is actually pretty important when you're doing parsing. And so Earley's algorithm with probabilistic forms can be pretty efficient, because you can look at the agenda and you can go, I can look at what I'm going to do next, and you can work out how you would order them to do them next. Okay? So what we've talked about today is context-free parsing algorithms, 2 in particular. We've talked about 2 choices of doing just recognition, is it in this grammar, like a language model, and we could do that either as full parsing, or we can do it probabilistically, so we can get full recognition, we can get the full parses, or we can do some probabilistic form to be able to get some number out of it, score, so we can sort them, okay? Sometimes you really just want the recognition, sometimes you want the probabilistic form and the recognition. That's sufficient. We're using it as a language model, try to score things. Imagine that you had a project that you were doing where you were generating questions from Wikipedia entries. I'm just selecting that as a random possible problem that you might know about. Okay, so imagine if you were doing that, and now somebody's telling you you've got to provide 50 questions, okay? Which of the 3,400 questions that you generated are you going to choose? Well, maybe the ones with a high probability for parse would be a good idea, because those are the ones most likely to be well formed, okay? So if you were going to do that, you could parse the sentence, the question, and get a score of how likely it is within the grammar that you're dealing with. Or if it's not in the grammar, you probably want to give it a score of 0. And then you could choose the top 50 with the highest probability, okay? And that's a perfectly reasonable thing to do. We often do that, okay? I also talked about Chomsky normal form versus generalized context-free grammars as a choice. From a computational point of view, or a theoretical point of view, it doesn't make any difference whatsoever. You can always convert the two, but sometimes it's easier to deal with context-free grammar rules that have got multiple 1, 2, 3 or more daughters in them, and therefore you might want to do that. Earley's algorithm is a good way to actually deal with that. The CKY algorithm or the CYK algorithm is a reasonable one if you're in Chomsky normal form. Often in machine learning, when we're learning grammars, which we do, there's a whole bunch of different algorithms for doing that, we often restrict the shape of the grammars that we learn to be Chomsky normal form. Partly because we're lazy, partly because it's a little bit easier to train, partly because we know fundamentally it doesn't make any difference on the complexity of the language that we can actually recognize, so we can get away with that. Okay? You can search the whole space for parsing, or you can limit it with interesting techniques, especially if there's an explicit agenda, and that's often a good thing to do. It might not be guaranteed to always get the best parse, but it will get the fastest parse, and that's something we care about. Okay, most people think that computers are so fast that we don't have to deal with it, but many of these things are in the squared or cubed space, and so you don't want that. And so often it's a good idea to not search the whole space, or to search the whole space, find the best one, and then find the best algorithm that gets you the best one almost every time. Okay, that's it for today. Okay, thank you.